Hello everyone and welcome to Engineer Tomorrow's 16th video in the Thermodynamics video series. Today the subject is going to be an introduction to specific heats, and this is the first part out of two videos. So first of all, what is a specific heat? So in thermodynamics we need a value that allows us to compare the energy storage capabilities between different substances, and that value is the specific heat. So more formally, this value is defined as the energy required to raise temperature of a substance more specifically of a unit mass of a substance. So let's say unit mass by 1 degree. Okay, so the specific heat can be listed as in Kelvin, Rankine, Fahrenheit, Celsius. And more specifically, there's actually two different specific heats that are often used in thermodynamics. So that is the specific heat with constant volume and the specific heat with constant pressure. So those are just exactly what they sound like. So the specific heat with constant volume, CV, is the energy delta E required to change the temperature holding the volume constant. Okay, so I'm just going to show you a quick little diagram of this scenario. So let's say we have an enclosure. Okay, and we draw our boundaries right there. Okay, and we have heat that enters our system like that. Okay, and what you'll find is that the internal energy, U, has a relationship with CV. But when you're looking at a closed system analysis, you tend to use the specific heat constant volume. But we'll explain that in future detail in the future videos. Okay, and next we have the specific heat constant pressure, and that's energy required for 1 degree change holding the pressure constant. So constant. Okay, so to follow what we did in the previous one, let's say we have a system and we have a piston. Okay, and we have atmospheric pressure. Okay, and then we add heat to our system. So this is our boundary. As we add heat to our system, this piston is allowed to move up. So the volume changes, but the pressure inside of the container matches the pressure on the outside of the container, neglecting the piston weight. Okay, and what you tend to find is that the enthalpy has a relationship with this specific heat constant pressure. Okay, so let's just look into detail at these these relationships. Okay, so let's say that we have a closed system, like the one we showed first. Okay, and let's do the energy balance for this relationship. So we have the change in energy in minus the change in energy out is equal to the change in energy in internal energy plus the kinetic plus the potential. But let's assume that those are equal. So we end up with this relationship. Okay, so using the definition of specific heat, we can actually incorporate that into this term right here. So this allows us to relate specific heats to the energy equations, energy balances, and other thermodynamic properties of a specific substance. So the actual relationship is the change in U, or the change in the internal energy, is related to the specific heat, constant volume, times a change in temperature. Okay, so if your change in temperature is 1 degree, this is the amount of energy required to change that 1 degree, and you end up with that change in energy right here. Okay, so you can rearrange this relationship to get CV is equal to du over dT. So that's the derivative of the internal energy with respect to temperature. Okay, and this is with constant volume. V constant. Okay, so now let's take a look at the other measurement that we had talked about. So we have a piston. We're adding heat to our system, and it's allowed to expand, and the pressure constant. Okay, so what is our relationship? We get change in energy in minus change in energy out is equal to dH plus, other terms which we're going to say are 0, so this ends up getting taken out. It's just set equal to dH. Well, what is dH? So from the definition of enthalpy is equal to the internal energy plus the pressure times the specific volume. Okay, so taking the derivative of this, dH, we end up getting du plus, using the product rule in derivatives, we get pressure times the change, or times d specific volume plus P times specific volume. Okay, but we just said that this term is going to be constant in our system. That's a definition we gave, so that it'll allow us to use specific heat. Alright, so let's neglect that. So we have this term right here, and we can plug that into the relationship up here. Okay, and so if we use the definition once again, but for the specific heat of constant pressure, we can determine what this value actually is. So to change the energy by 1 degree, we have to multiply the change in temperature by the specific heat, constant pressure. Now that'll give us the change in energy. So the change in enthalpy is what we'll end up getting, and Cp is related to the enthalpy in that equation, and we can rearrange that equation to get this P constant. Okay, so from knowing the temperature, now we can actually incorporate that into our energy relationship using the specific heat. So that's the overall objective of using this term. Okay, and that will enable us to get terms values such as enthalpy, the internal energy of the system, the specific volume, and the entropy, which we will be discussing later on, of a system by knowing change in temperature from one state to another. So there it goes. From one state to another. Okay, and just, I should have said this earlier, the units of specific heat are joules per kilogram Kelvin. Okay, and this term is similar to the ideal gas constant in terms of units, so you can think of it as that. And one last thing to state in this video, Cp is always greater than C specific volume. Okay, and the reason that is because there's an additional PDV term, which is due to the boundary work of the system. Okay, so you're going to have more energy for the specific heat constant pressure because you can get that change in volume. So there's an additional energy term added to your system. Alright, so I hope that was helpful. Please leave your comments in the comment section. Let me know if you guys need anything clarified. I'd be more than happy to do so. Thank you for watching.